Can you hear me? Okay, so I've uploaded the exercise question on Blackboard yesterday night. So if you haven't looked into the questions, you can have a look now. And we may start discussing after 5 minutes. Okay, I think we can start now. And let me share my screen. Okay, can you see the screen? Okay, so the first thing, just to remind you that assignment 1 has been uploaded to Blackboard, and the due date is 15th of February, so about 1 week time. And remember to submit it on time. And so before discussing the exercise question, first I would like to answer some of the questions that were raised last time. And the first one is about the structure of the Feynman diagrams. A student asked why there's only one allowed primitive vertex like this. And last time I said because other vertices may violate some conservation law, such as the charge conservation. But I think it's not so complete, because if you consider this vertex, it seems that it doesn't violate any conservation law, but still not a primitive vertex. And to understand this point, I think the most appropriate way is to go back to see the purpose of Feynman diagrams. So in particle physics, one thing that we do very often is that given the initial state and the final state of some particles, we want to obtain the transition rate. That means we want to know how likely the initial state will transit to the final state. And this is calculated by the so-called perturbation theory, which is a subject in quantum field theory. That means, let me write that down. That means the result can be written in a series like this. So it's like a series, and each term can be obtained by considering the perturbed Hamiltonian. So, but the mathematics is very complicated, but it's the basic principle, how we calculate the transition rate of a process. And because the calculation is very tedious and it's not so intuitive, so Feynman designed the tools of Feynman diagrams so that each term in the series can be written down easily by looking at the corresponding diagrams. And this is called the Feynman rules, which you will learn later in this course. And so Feynman diagrams is based on the theory of perturbation. So it's not the most fundamental thing. So if we include some vertex like this, then this diagram will not correspond to any terms in perturbation. And that's why we don't consider this as a primitive vertex. So I think it's a more complete answer to see why we only need one primitive vertex, because it's based on the principle of perturbation. And the next topic that I want to talk more is about the virtual particles. So as I've said many times, virtual particles are proposed to explain the interactions between the particles. And last time I forgot to stress the point that virtual particles will preserve most of the properties of the real particles, such as the charge, the spin. So for example, for a virtual photons, it will be have zero charge and spin 1. And the main difference between a virtual particles and a real particle is that virtual particles do not necessarily carry the same mass of the corresponding free particles. And this is the only difference between virtual particles and real particles. And there's even a phrase to describe this. We say that real particles is on mass shell and virtual particle is off mass shell. And to see, to understand this, you can consider a 4-dimensional phase space in which the axes are the 4 momentum. So if you consider this energy momentum relation, then the real particle will lie on the shell in a 4-dimensional space, just like the spherical shell equation in 3-dimensional space. So we say real particle is on mass shell and virtual particle is off mass shell. So back to the Feynman diagrams. Nowadays, the most acceptable interpretation is that in diagrams, energy and momentum are conserved in each vertex. And to achieve this, then these particles have to be off mass shell. And so that's why we come up with the concept of virtual particles, because we insist that energy and momentum should be conserved in each vertex. But there's also other interpretation saying that we insist every particle in the diagrams is on mass shell. That means they are real particles. But in this interpretation, we have to give up energy conservation in the vertex under the constraint of uncertainty principle. And if you remember, in exercise 1, we even use this interpretation to obtain the mass of the pions in nuclear force. So, but nowadays physics is love energy conservation. So, so the concept of virtual particles is more acceptable. So this another note about virtual particles. Okay. Is there any problem? The spin is also the same. For example, the photon. Photon is a more tricky example because normally photon is a spin 1 particles, but a real photon, because it's massless, so it will have there will be something called the gauge freedom. So after eliminating the gauge freedom, there will be only 2 polarizations. But for virtual particles, for virtual photons, it's also spin 1, but because it has mass, so you will have the complete free polarization. So the spin is also the same for real particles and virtual particles. Yeah, for example, the virtual electron, it will be also spin half. So the only difference is that virtual particles can have a variable mass. Okay, and so let's go to the first question. So the first question, we are asked to determine whether B meson will decay preferentially to D meson, kaons or pions. And the question asks us to consider the quark content. So we can first list all the quark composition of the mesons. And if we look closely, you will observe that for B meson, they will all contain a B quarks together with some U quarks and D quarks. And for the D mesons, you will observe that all of them contain C quarks plus some UD quarks. Similarly, for kaons, is composed of a strange quark plus the UD quarks. And for pions, is also some pickup of UD quark. And so if B meson have to decay into one of these, then the transition must involve a transition from B quarks to one of these quarks. So then we have to consider the cross-generation mixing in big interactions. So what is cross-generation mixing? So we can consider this charge-weak vertex. So initially there's a strange quark coming in. So if there's no cross-generation mixing, then the quark that's coming out should be a C quark. But in charge-weak interaction, we can have cross-generation mixing. And so the S quarks can transit to a U quark. So there's a transition from the second generation to the first generation. So back to this question, we start from a B quarks. So there are 4 possibilities. They can transit to D quark, S quark, U quark, or C quark. But we can first rule out the possibility of D and S because they are both they have the same charge, and so the transition will involve 2 vertices. That means if B wants to transit to S, then it has to first transit to C, and then from C transit to S. And that will involve 2 vertices. And so the diagrams are suppressed. So it shouldn't be the preferred way. So we only have to consider transition from B to U and from B to C. And then we can consider the CKM matrix. So the meaning of the CKM matrix is that the modulus square of the entries will be proportional to the transition probability between the 2 quarks. So we can consider these 2 terms, these 2 entries. So we can see VCB have a larger value than VUB. Then that means the B quarks will have a larger probability to transit to a C quarks. And so the answer will be the D meson because they are composed of C quarks. Okay, I think it's clear. So for the second question, is some practice about the Feynman diagrams. So we can first consider this muon decay. And first you see there are some neutrinos. So it must be a weak interaction. So we can draw the muon. And then in this vertex, we can draw the electron. So this is the diagram of muon decay. And in the question, we still have to add this electron-positron pairs. And the more straightforward vertex that we can think of is the photon vertex. Then we can connect this to the W boson because the W boson can couple with a photon. So this is one possible diagrams. And you can also connect this to the electron because the photon can also couple with an electron. But you cannot connect it to a neutrino because neutrino has no charge, so it will not participate EM interaction. So this is the first diagram. Okay, and for the second process, we can first see that they both have two U quarks. So we can simply draw these two. And then you see that there's a transition from S quark to D quarks. And just recall the quark model. So if the S quark want to transit to D quark, there's a cross generation. So it should first transit to U and then transit to D. So we can first transit to U, and then transit to D. And then you see that we can connect these two W boson so that you form a loop. So that's the W boson loop in the hint. And we also have the photons. So similar to previous question, we can connect it to the W boson. In principle, you can also connect it to the quarks, but most people would connect it to the W boson. So this is the diagram for the second process. Okay, and so let's look at the next question. So this question is asking about the psi prime meson. It has the same quark content as the gypsum meson. And in fact, psi prime meson is an excited state of the gypsum meson. So it would decay back to the gypsum meson plus some byproducts. So we are asked to determine whether this process is OCI suppressed or not. So again, we have to draw the Feynman diagrams. So just to remind you that the pion composition is like this. So we can first draw the two C quarks. And we can see that there's a UU bar and DD bar in the final state. So we can draw like this. So this will be the positive pions. This will be the negative pions. And then we can use the gluon line, connect it to the C quark. You can also connect it to the C bar. It's also acceptable. So this is the diagram for this process. So the next step is to determine whether the process OCI suppressed. And the simple way is to see whether the gluon lines are all connected to the final stage. That means if the gluon lines is something like this, this is the final stage, then it's OCI suppressed. And if you see something like this, then this is not OCI suppressed because there is one intermediate state which share the energy with the gluons. So it's not OCI suppressed. And so you can see that in this diagram, all the gluon lines are connected to the final stage. So the diagram is OCI suppressed. And just to revise the argument, we call that one Feynman diagram correspond to one term in the perturbation, and one vertex in a diagram will mean that we have to multiply one coupling constant in that term. That means if there are two vertices, then this term will proportional to alpha square. If there are three vertices, then you proportional to alpha cube. And one special thing about strong interaction is that the coupling constant, that's the alpha, will decrease with gluon energy. That means when the gluon energy is high, the coupling decrease, which is different from EM interaction. So we say gluons couple weakly at high energy. And if the gluons is all connected to the final stage, then the gluons will have a high energy. That means the gluons will be hard. So the coupling constant will be small, and that means this diagram will contribute a smaller term in the perturbation, and that means the decay rate will be smaller, and so the lifetime will increase. So for a strong interactions, the time scale is about 10 to the minus 23 seconds. But due to the OCI suppression, it will be about 10 to the minus 20 seconds. So this will be approximately the lifetime for psi prime meson. So we can go to the last question. So the last question asks us to draw this process first. So to remind you, the proton is UUD and the pion is UD bar. So I think most of you will draw something like this first. And because we want to produce a W boson, so we can consider the transition from D to U. So And we also need a D bar. And if you look at this, you see that we can use the D bar here. So this will be the pions. Then you can notice that you can connect this to U quark like this. So if you draw more beautifully, we can draw like this. So it seems that this is the final diagram, but there's a problem in this diagram. If you consider these two U quarks, it will mean that a U quark and a U bar quark annihilate and give out nothing. So this will violate energy conservation, and so we have to add some additional gluon lines in this vertex. So that the U and U bar can annihilate to give out some energy. So this final diagram of the process. So, and we are also asked to explain why pion is a more preferred candidate for X. And the reason is quite simple, because in principle, if the mass difference between the final state and the initial state is large, then it means this process will be more kinematically favored because there's larger phase space available. Yeah, the phase space just means the four-dimensional space formed by the energy and momentum. And if the mass difference is large, that means the final particles can have more freedom to choose their energy and momentum. So the final possibility will occupy a larger volume in this space. And in opposite, if the mass difference is small, then the final particles have little freedom to choose their energy and momentum. So they can only have a smaller choice for the energy. And so that's why a larger mass difference will mean more kinematic favor. And so that's why pion is more preferred, because if there's other species or more particles, then the mass difference between the initial state and final state will be larger, and so they are not preferred. So this but I would like to remind you that there's one very famous exception to this principle. That's the pion decays. So if you consider these two processes, according to this principle, you will say the electron channel will be more favored because electron is lighter than muons. But the experimental fact is that the muon channel will have is much more preferred than the electrons. And this is due to some unusual properties of neutrinos that you will also learn in the later course. So I don't explain much more detail here, but you have to remember there's an exception to this principle. So I think that's all about the exercise. And you may leave if you have no questions. And if questions, you can raise. What is OCI suppressed? Okay, so maybe I can repeat once again. So OCI suppressed. So normally for a strong interaction process, the lifetime will be of the order 10 to the minus 23. But for some strong process, the experimental result saying that they are just 10 to the 20 second, and that's several order longer than the normal time scale. And the reason is the OCI suppressed, which is explained in this last in this sentence. So if the gluon lines are all connected to the final stage, that means like this. Then the gluon will be have a higher energy than in this case. Because in this case, there's a intermediate state which can share the energy with the gluons. But in this case, the gluon energy have to provide the energy all by itself. So in this case, the gluon energy will be high. And in strong interaction, when the gluon energy is high, that means the coupling constant decrease. That means this Feynman diagram will contribute a smaller term, and so the decay rate will be lower, and that means the lifetime increase, and we call this argument as the OCI suppression, the OCI mechanism. Okay, is it clear? Okay.
Can I ask a few questions?
Yeah.
Well, the psi prime, the Feynman diagram of psi pi transition, sorry, the decay, psi pi decay.
Yes.
There were two gluon lines which you drawn connected to the same charm particle.
Yes.
I'm thinking, what if I change, I connect one of those gluon lines to the other charm particle. You said it is, is acceptable, but I'm thinking,
it's acceptable. Yeah, same case.
Yeah, but would it change like energy content, or would it like what is happening? Because the first one, that when you connect two gluons to the same charm particle, that would means during this charm to charm decay or this transition, there are two gluon shooting out of the transition. But if you connect one of them to the other charm particle, then will it be more favorable to one or the other?
I see your point. If you want a rigorous proof, then you have to know to calculate the terms according to Feynman rules. But I would say they will. I would say they are more or less similar, because if you count the vertex, in these two cases, they all have two vertices. So, and the initial state are the same, and the final state are also the same. So the only difference is how they connect in the middle.
Mm-hmm.
So I think they will be not different, no difference in here. But for regular proofs, you have to use the Feynman rules.
Okay, so apparently it's suggesting,
but they must be of the same order, because they both have two vertices in the diagram.
Right. What if this thing happened? Like, if I don't consider like just some mesons decay, so what if I also consider like background particles? Like, there are many floating, like let's say there are many charm particles floating around, then you can add like 100 more of those charm to charm transition lines, right? You can just add them together as a so-called background. Well, then in that case, I can have 100 of those gluon lines coming out of the first branch, and yet it wouldn't change anything, would it? Because you said, so this is what I'm saying. Let me draw.
Okay.
So what if I have like 100 more of this charm to charm line, and then like 100 more, and then I can now argue that you can have 100 more of these gluon lines sticking out of this same process, because you can as well join these gluons to here, and the same Feynman diagram doesn't change.
Well, then in this case, you are not considering this process, because if you add more lines, then that means you have some more initial states and final states.
But there's a background particle just floating around doing nothing.
Yeah, then that means you have changed this process. You have to add some additional particles to this.
But they just come out from the same. But they will also come out from the other side here, right?
Yes.
So
So they are not the same process. If you're just considering this initial state and final state, then we just have to considering two charms. If you add more charms, then you just considering another process by including the background particles.
Okay. Okay. So
Yeah, you're correct. If there are more charm particles, then they can connect to this, but then you are not considering the original process.
Then how does, like in CERN or in whatever particle collider, how do they make sure the particles do not interact with the background particles? Like, you know, charm just floating around. I can, yeah, that could happen, right?
Yeah, that could happen, but let me see. Yeah, in CERN, in principle, we have some isolation requirement. That means you want to really look at the track and to make sure that they are well separated from other jets, for example. So, for example, we can calculate the angular separation between a track and a jet, and to make sure they are large enough. And so we can eliminate the effects of the background particles. That's basically a simple way to do it.
Okay.
Yeah.
Thank you.
Yeah, you're correct. There are many backgrounds, and one of the major work is to eliminate this background so that we have a clean signal in our detectors.
But that is interesting because, I mean, these charm, they could, I mean, you can have those pair production and pair annihilation. So you can just out of vacuum, suddenly it pops up a particle and then disappear again. So I was thinking, how can I make sure that the particle that I'm colliding do not interact with these like pair production and annihilation particles in the middle?
Well, if you are saying pair production, then you are saying internal lines, right? You are saying something like this.
Yeah.
And then they are internalized. Then they are the higher order diagrams.
Oh, so they will be something on that. Okay.
Yeah. Then they will contribute as a higher order diagram.
I see. There is the other one related to the next question about the boson, the W boson. So my question is basically, why can that W boson stand alone? Because you would, at the end you said because of energy conservation and stuff, you would want the U to NTU, that transition, have a gluon line connected to the D to U line. Yeah.
Okay, something like this. So you are asking?
Yes, this, yes, exactly. Yeah, and because intuitively I would connect that particular line, this one, to this emitted gluon, because I mean, because the D to U one, this D to U, it is a fundamental vertex, right? And it has a gluon line here, and now you have another gluon line here. Then I would intuitively join these two lines together. Like, but why wouldn't that happen? Or why does the W can stand alone?
W can can stand alone in principle because it's not like the gluons. The gluons you cannot exist alone. But for W boson, you see, so let me say in this way, in experimental sense, W boson will first decay into a lepton plus a neutrinos.
Okay.
So for example, electron and a, so that's what that's how we detect W boson. We cannot we do not detect them directly, but detect the decay products. So, and about the connection of the gluon lines, I'm checking the slides. It seems that we cannot couple a gluon to a W boson. So,
Wait, but aren't those two lines are the same gluon lines? Am I? I'm sorry. I'm so sorry.
yeah, this is gluon and this is W boson.
Yes, one is the strong interaction, the other one is
Yeah.
I'm sorry, so sorry. Just before I continue, are there any other questions from others? I'm afraid someone may have some questions.
Yeah. Yeah, very good question.
Thank you. But if no, then I will continue. So the other one is about the very at the very wait, hold on. Am I? Yes. At the very beginning, when we go back to the previous exercise class, when we talk about the Feynman diagram and allowed vertices, virtual, yes, exactly here. You said those two are not primitive vertex because they are not the perturbation terms. But then now the question would then becomes, why aren't those some allowed perturbation terms? Like, is there any physical reason those aren't the perturbation terms? Like charge in not conserved is probably one reason, but the other one, why couldn't it be a perturbation term, basically?
See. To be honest, I have to say I'm not so familiar to the exact calculation of the perturbation, but I can, if I remember, the way is to write the Hamiltonian as some perturbation, and then we obtain the time translation and then act on the initial state, and then find the transition rate like this. So this will be some series. So this the so this the basic principle, and you're asking why is this, and I would say I would say that's how the nature works.
Okay.
Yeah, to my level, I would say like this.
Okay. Never mind. Yeah, I think that's probably it. Yeah, that's it.
Is there any more question? The mass difference. Okay, so the basic idea is in fact quite intuitive. For example, you can consider the decay of a particles. So if the mass difference between these particles and this particle is small, then that means these final states have very little choice to choose the energy, because the energy have to conserve. If their mass difference is small, then they cannot be very high energy, because then that will mean they will have larger energy. So on the other hand, if the mass difference is small, the mass difference is large, then the final state can have more freedom to choose the energy and momentum, because even when the energy is larger, they can also equal to the initial energy. So that's about so in simple words, that's about how the final state have the freedom to choose their energy and momentum. Is it clear? Well, I think it's not so related, because in this question, we are just asking why X is more favored to be pions. And if it's other thing, I don't know if they're like this, then the mass difference will be smaller. So this is not favored. And I think it's not related to W boson. In principle, if the proton energy is large enough, then you can produce a W boson. Yeah.
Just a very subtle thing. In the slides, for different interactions, those gluon bosons line, they are drawn differently. Like one is more spiral, like the other one, for the EM interaction is more curvy, wavy line. Does it matter actually?
It's just a pictorial way to
Yeah. I'm saying, does it matter when I draw, like on exam or in midterm, whatever?
I don't know. But my suggestion will be to follow the slides. the lectures, follow the notation.
Okay, because I find the glue online and both online is a little bit hard to distinguish.
Yeah, but it's better to add some to add the character here.
Okay, okay.
Yeah.
Thank you. Thank you.
Okay. So if there's no more question, then we can stop here and goodbye.